Okay, first an announcement. The homework is due Tuesday, not tomorrow. I'll fix that mistake in the website. Also, I think the password has been activated for the site. So the login is Maram, M-A-R-A-M. It's the name of Shri Stoddard. And the password is Maram. You remember one, you remember both. And two M's in Maram. M-A-R-A-M. So any questions from last time? Okay, so last time we ended with the iterative least squares gradient code, or steepest descent code, sometimes most often called. And just a quick review, all you do is you take the residual and you apply the adjoint, or in this case the transpose specification of adjoint, to the residual, and then you hit it with a scalar step length, and then you adjust the old possible solution in this way, and you get the new one, and then you repeat that. And the pseudocode for that is given the data, the measured data on the right-hand side of the main set of equations, system of equations, and given a starting model M, you simply have a loop that goes through taking the new predicted data. Here's the starting model, so you apply the L to it, the forward modeling operator, say, and get the predicted data. Then from that, you update the residual, and then you apply this formula. Notice that in the code, your MATLAB or your Python codes don't have superscripts or subscripts. So you simply redefine the M as the new M there. And then you stop after a sufficient number of iterations, and that's when the RMS residual, that is the sum of squared errors, normalized by the number of residuals there are, falls below some threshold. Any questions on this? So what's the problem with this, Abdullah?
It's fine.
It's fine? You're happy with it? There's no problem with it if your contours associated with your misfit function are like basketballs. But if your contours are oblong, like American footballs, then what's the problem?
Oh, you have so many to do a minimum.
Yeah, you're moving in the wrong direction. And you're moving in the wrong direction for at least a linear problem, because you approximated what should be what should actually be here.
Inverse of if x by x the
So
square matrix.
and we're going to call that Hessian.
Okay. Yeah.
So L transpose L is a Hessian, or depending on what problem it is, X transpose X is a Hessian. So we said, now, what was our approximation, Marco?
One of
What?
the approximation.
Yeah. What allowed us to replace that guy with an identity matrix?
The dominant.
Diagonally dominant. And we said all the diagonal components were about the same. They weren't the same, that they're different, but they're still diagonally dominant. Then you have a matrix, instead of an identity matrix here, which you don't see, it's invisible, it's implicit. That identity matrix is replaced with an inverse of a diagonal matrix, which is trivial. And that's called precondition, which we're going to talk about now. Okay, so let's talk about this problem, what we call ill-posed system of equations, and how one partial remedy. So our old system of equations was given by this, and it was inconsistent, but the eigenvalue associated with it pretty, at least for the Hessian, is pretty good. That is, the condition number was very good for that. Now we're going to set up a system of equations that's ill-conditioned. And we also call that an ill-posed system of equations. Still the same number of equations, same number of nodes, but now we're going to change them. So we're changing them to that. In this case, notice that the columns here are almost identical. Not quite, but almost. So to go ahead and plot out this equation overlaps that equation. Say, this one. But this last equation is almost identical to the other two in terms of the slope and the intercept, except it's slightly different. And we're going to assume it's consistent in this case. So they have a common intersection point. Okay. So the error here is what? It's a consistent set of equations, Marco. The error at this point is what for the sum of the squared errors? Zero. So you have a big kind of a bowl surface that kisses the zero error plane, and it's where it kisses is right there. On the other hand, if you have a solution here, it satisfies one of the equations, but not the other one. So what kind of error are we talking about? Give me a number.
0.2.
0.2?
1,
0.0002. Because notice that this potential solution
it's close.
is close to the other line and almost satisfies it. So the error is very small. In fact, the error is very small for almost any potential solution, partial solution here. So the error bowl now, instead of being a big basketball, it's going to be kind of a elongated ellipse. So let's plot up that error bowl associated with system equations where the column vectors are almost identical in this particular case. You know, like that. And this leads to the problem we saw with the previous slides on trying to use the steepest descent to get to the optimal solution. So let's flip that around by 90 degrees, and that's what the error surface looks like. And so many of these solutions here, potential solutions, well, they're not exact solutions, but they're, within, because we have errors in our data, there could be, if we take the exact solution, that may not be the one we want because of the errors on the right-hand side. So small errors on the right-hand side could potentially lead us to solutions that are very far away from the original one. And these errors are always in our data, so we have to consider all of these potential solutions along the main axis, along this inner ellipse to be potential solutions that are useful. So which one is most useful to you, Marco? One's way out here, one's way over here.
That's close to, awfully close to the main.
And why very close to the origin, you say? Why?
Because it's going to be faster.
Say what?
Why closer to the real point?
Yeah, why would you want your solution to be closer to the origin? What's a physical reason, say a particular example problem that you might be working on?
I don't know, a system of equation like the velocity or slowness, travel time, and I want to have some points that is going to be close to the real mean.
Something reasonable, like, velocity of P waves in sediments, 2 kilometers per second, which might be over here, but not way, way over there. Okay, that's ridiculous. So he's choosing something that's a rather small velocity. So what he does is impose a nudge to the system of equations that tries to encourage it to, if you're going to find a solution within this inner ellipse here, let's get one that's near the origin. So we're going to add a penalty term for a system of equations. And that's going to be called regularized least squares. And the solution will be iterative least squares, regularized least squares. So you have two terms here. Here's our old friend, which is the data misfit function. And then we have another guy here. And that's a model penalty function. Why do I call that a model penalty function, Marco?
How I call it? Regularization.
What?
How I call it?
Why do we call this a model penalty function? We call this a data penalty function because we wanted an M that originally, without this right-hand term, we wanted an M that minimized the data misfit. So if you got an M that had a large data misfit, you were penalized.
Yes. And then instead I want to analyze the parameter of the model.
Okay, so now you want to also make sure that M is small, because any M that is large, you're going to be penalized with a large epsilon. And the mediator between, so you have a balancing act between trying to satisfy the small model, but at the same time having a small data residual, and the mediator between those two almost contradictory demands in some cases is a lambda. The larger lambda is, you emphasize the model penalty function, and the smaller it is, you emphasize the data penalty function. And how you find that is by experience and trial and error typically. So let's go through what we did before in terms of finding what the gradient is if we have some guessed solution out here. We go ahead and find the gradient associated with the new misfit, or new, we're going to call this objective function. Before, when we just had that, we called it the misfit function. When we add the not model penalty function, we now call it the objective function. So let's take the gradient of the objective function and see what it is. And we can do this by, I think you should be able to do this by just visual. In your heads right now, you take the derivative of this guy with respect to M. You have to first get that guy, then you get that guy, and you add the two results up, and that takes care of the 1/2. So let's rearrange this equation. And what's going to happen is we see a common term here. M is common to this term. So let's combine this term with that, and you're going to get an L trans. This is an identity matrix. See it? You combine this term with that term, you get L transpose L plus identity times lambda, and then that sum multiplied by M. Then you rearrange things, and you get that. Take the inverse. So you go ahead and set this equal to 0 and solve for M, and you get this as a formal solution. We knew what lambda, we knew what the gradient looked like at this point alone, just with the data misfit function. It pointed perpendicular to the tangent to this point. So the question is, where does this point? Well, let's look at the end members of this guy. That is, when lambda is really, really, really bigger than this, we can ignore this guy. Then this is the only term that counts in terms of this. This is so much bigger, this lambda is so much bigger than any term here. We can reduce this guy just to something that's proportional to L transpose delta D scaled by 1/lambda. We're looking at directions now. So when lambda is quite large, it tends to be the direction of the downhill direction along the gradient. When lambda is equal to 0, this guy reduces to our familiar form of the new move direction. And what direction should that be, Marco?
The steepest.
If you're right here, where should be the delta M pointing?
Should be orthogonal to the contour line.
No, this is orthogonal to the contour line. This is the gradient. Right?
Deviation multiplied by.
But if we take the Hessian inverse and multiply it by that gradient, what direction is it pointing? Anybody?
So it should be pointing to the maximum perpendicular to the contour.
The gradient is perpendicular to the contour.
Yeah.
This is the gradient. This is not the gradient.
Okay.
Who's taking this class for credit? Look, man. Where is he pointing?
In the direction of the gradient itself.
No. The direction of the gradient is perpendicular. It doesn't look like it's perpendicular. It is. Take the tangent take the perpendicular, that's going to be that time.
Probably pointing to the original gradient.
And so Chu Yu says it goes towards the bullseye. Why?